Today, you're going to learn theorems and learn to write proofs that deal primarily with angle congruency. The vertical angles theorem is actually one of your most useful theorems for the entire rest of the semester. The vertical angles theorem says that when you have two vertical angles, in other words, two angles whose sides are made of opposite rays, like 1 and 3 and 2 and 4, those pairs of vertical angles will always be equal to each other, or congruent. So when you look at angle 1 and angle 3, you can mark those congruent on your diagram because they're vertical angles. An informal way of thinking about vertical angles is that they are angles that are opposite sides of an x. So 1 and 3 would be congruent because they're vertical angles, but you could also say 2 and 4 are congruent because they are also opposite sides of an x. They are also vertical to each other. Remember to take very detailed notes on the theorems and postulates, including the diagrams there. So you can use vertical angles theorem to solve questions like number 1 and number 2 here. For number 1, because we have two angles that are vertical to each other, we know they're equal. So we could say 3x minus 40 equals 2x minus 10. A quick note about the parentheses. In a lot of diagrams where they have an actual equation where an angle goes, there are parentheses there really just to show that the degree symbol applies to the whole thing, that the degree symbol would not just be on the 40, but on the whole 3x minus 40 quantity and its answer. Since there's nothing outside the parentheses to distribute, you can kind of ignore them. They're really just there to say that degrees apply to the whole thing. Go ahead and solve for x. So you notice that you had x in two different places in your equation. So you had to get them on the same side of the equal sign. A quick note, make sure you don't lose negative signs. Minus signs become negative signs if there's nothing in front of them. So this is still a negative 10. Watch out for that. Don't lose that negative sign. To get x all the way by itself, you canceled out the minus 40. And you got your answer was x equals 30. Try question 2. Check your starting equation. You had to get the x's on the same side of the equal sign. Then you had to isolate x, so that meant canceling out the minus 27. And then get x all the way by itself by dividing by 3. If you got 13, well done. A quick note, notice how these problems are not asking you to prove what the answer is, they're just asking you to solve. When you have a question asking you to solve, you do not necessarily need to show every single detail of the work that you could do in your head, like you would with a proof. So it's okay to streamline this. So when I'm looking at your homework, I'm primarily checking that you have your initial equation, some of the work, maybe there's 1 or 2 steps you did in your head, and your final answer. The most important part is the initial equation. You could streamline the work and not necessarily show all the details unless it's asking you to prove. Go ahead and try question number 3. So you may have noticed that the 3x plus 10 angle and the 130 angle were vertical angles to each other, so they had to be equal. So you minus 10 from both sides, divided by 3. If you got x equals 40, well done. Now y is a little bit harder because there's no vertical angle opposite of y. However, looking at the picture, I want you to notice that y and the 130-degree angle it's next to make a straight line. How many degrees are there in a straight line? 180 degrees. So you could say that y and 130 combined equals 180. In other words, y plus 130 equals 180. So y would equal 50. Now that you know what both of the variables are, you can go ahead and plug that back in and figure out the measure of each angle. So the easiest way to do that is to just copy the x made by the intersecting lines The important thing I want you to notice here is that when you plug in 40 where x used to be and 3x plus 10, it gets you 130. It does equal its opposite. And then if the top angle is 50, so does its opposite angle. Its vertical angle has to match. Next, we're going to cover some other theorems that have to do with angle congruency and angle equation forming in general. They're not quite as commonly used as vertical angle theorem. That's the most popular theorem for today in terms of how often you use it to solve proofs and problems. But you will need them, if not quite as often. The congruent supplements theorem says this: if two angles are supplements or supplementary of the same angle or of congruent angles, then the two angles are congruent. That sounds really confusing at first. So here's a quick example. If I know that 1 and 2 are supplementary, if I squish them together, I know it makes a straight line. It makes 180 degrees, and visually it makes sense that they would squish to make a straight line. But I also know if I picked up angle 2 and plopped it over here, it would make a straight line with angle 3. The only way that's possible is if 1 and 3 have the same number of degrees. Angle 2 can only be supplementary with both of them, can only make 180 with both of them if 1 and 3 match each other. So that's your conclusion. Because they're both supplementary with angle 2, angle 1 is congruent to angle 3. Remember to always take detailed notes on the theorems and postulates. Congruent complements theorem is similar except with complementary angles. The name of this theorem always makes me smile because usually we use complement in terms of saying something nice about someone, but here complement is referring to complementary, things that add up to 90 degrees. Congruent complements theorem says if two angles are complements of the same angle, or of congruent angles, then the two angles are congruent to each other. So here's an example to make sense of that. If you know angles 1 and 2 are complementary, you know that if you squish them together it makes 90 degrees. But you also know angle 2 and 3 are complementary. If you picked up angle 2 and plopped it over here, it would make 90 degrees with angle 3 as well. The only way it can make 90 degrees with both angles 1 and 3 is if 1 and 3 are this exact same size to each other. So, conclusion, angle 1 is congruent to angle 3. Next, angle theorem. This is called Theorem 2-4 in our textbook. Theorem 2-4 says that if you have any two right angles, they're automatically congruent to each other. This is one of the theorems that always makes me laugh a little bit because it's one of the laws of math that's so obvious. You're like, why did they even make this a law? Of course, if they're both 90 degrees, they're equal to each other. They're congruent angles, obviously. It's so common sense. Why is it a law of math? However, despite being kind of saying the obvious, this theorem is very useful for certain types of proofs you're going to learn in the next couple of chapters. So it's important for you to know because even though it's stating the obvious, it's a reason you could use for writing proofs very often. Because they're both right angles, they're officially congruent to each other. Last theorem for today, Theorem 2-5. If two angles are congruent and supplementary, then each is a right angle. So demonstrating that, here we have a diagram, and all we know is that angles 1 and 2 make a straight line. In other words, they're supplementary. They make 180 degrees. And we also know that 1 and 2 are the same size. They have those congruency symbols on them. If they're the same size and they add up to 180, they have to both be 90 degrees. That's the only way they can be equal to each other but still add to 180. That's what this is saying. Because angles 1 and 2 are both supplementary and congruent to each other, then they must both be right angles. So that's your list of theorems that have to do with angles. And you'll be using that for writing proofs both on today's practice assignment, but also in the next chapters, because in future chapters you keep using old theorems and postulates as reasons on proofs. So you want detailed notes on these theorems so when you look back on it during chapter 3, chapter 4, you can be like, oh yeah, that's the theorem I need. Now, following today's theme of solving angle problems, There's one type of angle problem that's going to be in word problem format that you will see a lot of today. So sometimes when you have a word problem, the best way to go about it is to translate it word for word into math. So here's number 4. Angle A is 2 times the size of its complement, angle B. What is the measure of each angle? Now, if you go through and think of math as its own language, often you could translate normal conversational language into math just by translating word for word and keeping the order the same. If we look at this bit here that I have underlined, A, we can, in math, just keep that the variable, A. Is, what does is translate into as a math symbol? If you said equal sign, well done. 2 times 2 multiplied by angle B. So really, when you translate that first sentence, it becomes A equals 2 times B, or just to summarize, A equals 2B. Now, that one equation isn't quite enough for us to solve because it has 2 variables. A rule of thumb is that if you have 2 variables in a problem, you need 2 equations to solve it. So we need a second equation. Let's look at our word problem again. Oh, there's one word in that word problem that actually tells us a lot of information. Complement. Complement, referring to complementary, means that A and B have to add up to 90 degrees. So that's our second equation, A plus B equals 90. Now we have our 2 equations, and you're going to use a technique you learned last year in algebra to combine them. So right now, you cannot solve either equation because you can't solve for A or for B when there's another variable there. You can't figure out what they are. So we have to figure out a way to write a single equation that has only one variable, only one letter in it. Here's how you could do that. You know how your first equation here is that A equals 2B? That means we could plug in 2B where the A in the other equation is. If A really equals 2B, just replace A with 2B. And now you have an equation that has only B's. That makes it possible to solve because 2B plus 1B is 3B. And then you could divide both sides of your equation by 3. And get that B would have to be 30. So just a quick note, this idea of saying, well, if A equals 2B, I could plug in or substitute 2B where A used to be in my second equation. That's the substitution method that you learned last year for solving systems of equations. Now with a word problem, you always want to go back and reread the question to see if you're done. What is the measure of each angle? We're not quite done. We figured out B's measure. We still need to figure out A's measure, but that's much easier than solving for B because if A equals 2B, and we know B is really 30, we just plug in 30 where B used to be. So A would be 660, B equals 30. You could always check your answers for the angles and see if they really do add up to 90 degrees. 60 plus 30 are complements of each other. It does equal 90 degrees. Now you're going to practice that technique. See if you could translate this into 2 equations. The measure of angle A is 1/2 the size of its supplement, B. If A is 1/2 of B, A equals 1/2 times B. There's your first equation. And then supplement refers to supplementary, which means that A and B add up to 180. Now you can say, well, if A really equals 1/2 B, I could replace the A in the second equation with 1/2 B, and it would still be a true equation. A quick note, when you have this equation here, some people find it easier to treat 1/2 B as 0.5 B. So if you want to rewrite it as a decimal, it might make it easier for you to do the adding. And don't forget, if you have a variable like B with no coefficient, it really means it has an invisible 1 coefficient. Now you can add those like terms. And to solve for b, you would divide both sides of your equation by 1.5. b equals 120 degrees. Now you could say, well, if I know what b is, I could plug that in for b in my other equation. 1/2 times 120, or really just 120 halved divided by 2, a equals 60. Next, we're going to practice proofs that focus on angles. Good news, for the first one, I'm actually giving you the statements half of your proof. Your job is to fill in the reasons. Pause the video here and figure out as many reasons as you can. Step 1, your reason was given. A quick note when you're writing proof, it's always a good idea to label the information it gives you on your diagram. 1 is congruent to 2. You can add those angle congruency symbols. Step 2, 1 is congruent to 3. Now when you're writing proofs, well, often a step is building on the step above it. Like usually for step 2, we look at step 1 and wonder, how is it building off of step 1? But it doesn't always build off of the previous step. This is one of the cases where step 2 is not building off of step 1. Instead, it's building off the diagram. So let's mark in the diagram what step 2 is talking about. So step 2 is saying angle 1 is congruent to angle 3. So we need to look at that picture and figure out how they knew angle 1 had to be congruent to angle 3. Oh, they're vertical angles to each other. They're opposite sides of an x. That's how they figured out that 1 and 3 were equal angles. Vertical angles theorem. Now, step 3 might be the hardest part of this proof because if you look at what they're talking about, 2 is congruent to 3. Well, vertical angle theorem doesn't work because they're not opposite of each other. So it's not straight from the diagram. And it is building off the previous step, but in a weird way. It's actually building off of both the previous steps to get to the conclusion that angle 2 and angle 3 are congruent. Look at steps 1 and step 2. Do you see any part of those two equations that are identical to each other? See how angle 1 is in both equations? What they did for step 3 is they said, well, if angle 2 is equal to angle 1 and angle 3 is also equal to the same angle, 2 and 3 have to equal each other. So they kind of just took out the repeats and put together what was left. There's a property you learned a couple lessons back that lets you do this and say if two things equal the same thing, then they equal each other. Transitive property. And because you have congruency symbols, it's transitive property of congruence. If it was an equal sign, you could get away with just saying transitive property done. But if it's congruency symbols, you have to be a little bit more specific. Step 4, if you look at your diagram, 2 and 4 are vertical angles to each other. So that's how they figured out that equation. It's vertical angles theorem. For step 5, look at steps 3 and 4, see if there's a part of those equations that's repeating. They said, well, if angle 3 and angle 4 both equal the same angle, then angle 3 and angle 4 have to equal each other. So they essentially took out the repeats there and squished together what was left. That is another transitive property of congruence. Sometimes you use the same reason multiple times in the same proof. Next proof. Step 1. Always a good idea to label on the diagram what the given tells you. Angle A is in the lower left corner. Angle BDA is the V here. So it's BDA would be talking about this one here. So you want to mark those congruent with those angle congruency symbols. And then write that down for your given. Now our end goal is to solve for x. To do that, we need to make an equation that somehow relates this 11x plus 20 to this 12x plus 15. But right now, we don't have any reason in our picture that we've shown that they have to be related to each other. So we need to figure out other pairs of angles that would be related to each other besides just these two. So let's look at this angle here. In the diagram, can you find another angle it would have to equal? If you said it would also have to equal its vertical angle, well done. Vertical angles are always equal. So if this is 12x plus 15 here, then this is 12x plus 15 here. Add that to the picture, and then we could write that down for step 2. We can say that angle BDA is equal to angle CDE. I want you to notice when we change how we name angles from using 1 letter to 3 letters. With angle A, we could get away with calling it just A, because it's the only angle that has a vertex at A. But for BDA and CDE, they both start at D, so we can't call them both angle D. That would just confuse people. They'd be asking, are you talking about the left angle D or the right angle D? So that's when you use a 3-letter version of an angle name to specify which angle you're talking about when multiple angles start at the same place, at the same vertex. All right, so the reason why you could write that these two angles are congruent is vertical angles theorem. Now in this proof, I'm just going to also demo some of the common abbreviations people use when they're writing reasons. It's totally okay, for example, to abbreviate theorem as THM. That's not uncommon. You could either write it out or abbreviate. I'll show you some of the common abbreviations in the next reasons too. Now, if you look at steps 1 and 2, do you see a part of those equations that is there twice? So both angle A and angle CDE equal the same angle, so they must be equal to each other. What reason is that? If you said transitive property of congruence, because since there's congruency symbols, well done. This is another common abbreviation you're allowed to use. You could either write out of congruence as words, or you could say of congruence using the congruency symbol to save some space. That's fine too. Now, there's a limited amount of properties we can use to solve an equation that has a congruency symbol. We can use transitive property, reflexive property, and symmetric property, but nothing else while there's congruency symbols. So let's rewrite that with an equal sign so we can use more properties. Measure of angle A equals measure of angle CDE. That would be definition of congruence that lets you rewrite it. If your angles are congruent, then their measures are equal. You can keep using congruency symbol as an abbreviation of congruence. Definition of congruency symbol is just as good as definition of writing out the word congruence. Now, you're nearly done, because here's the thing. If you have an equal sign, that means you're allowed to use properties that let you manipulate your equation. So you know what measure of angle A is, at least in terms of an equation. You could say measure of angle A is really 11x plus 20. And you could say the measure of angle CDE is really 12x plus 15. So you're replacing those parts of the equation with the equations they stand for. Now, when you replace something, when you plug in for something, what property is that? If you said substitution property, well done. You could always abbreviate property as just prop. That's fine. A quick note, technically, it's substitution property of equality, but most people will skip writing of equality because everyone assumes you mean the properties of equality if you have nothing there. You just have to be specific if you're talking about congruence. Properties of congruence are more rare, then you need to be more specific what type of property it is. All right, now you could solve for x. You have x's in both sides of the equal sign, so you might need to move one to its opposite side of the equal sign. It doesn't really matter which one, but I usually choose a smaller one, like I chose to minus 11x minus 11x. Some people will choose to minus 12x minus 12x. That's equally good. And that would be subtraction property. And then to get x by itself, you can subtract 15 from both sides. That'd be another subtraction property. And then you want your final step to match what you're trying to prove exactly. So let's flip that equation backwards. What property lets you do that? Symmetric property. Well done, everybody.